Good morning, everyone. Welcome back. Crazy how we're doing this every day, huh? Well, today we're going to keep talking about math. That's going to be the thing for the next 2 weeks. And in this lecture, we're going to sort of see the first truly weird proofs. If you get to the end of the course and then revisit these, they will seem easy, but it's going to be a way of thinking that you probably haven't done much of before, even if you've taken a discrete math course. You'll see why soon. But before that, we've got just a couple examples to warm us up, so try to go along with this. Try to go faster than me, but I'll guide you all through it. Oh, and if we have time at the end of the lecture, I'm going to go over the first assignment for this course, and it'll be posted shortly either way. So this example is sort of a review of mathematical logic. We have statements P, Q, and R, and a few assumptions that we've made. P implies Q. So if P, then Q. Not Q, so Q is false. And Q or R. So at least one of Q and R are true. They can both be true. Maybe just one, but definitely not neither of them. And we have to figure out, of the four statements below, which one of them is false. So for the first one, R, this is sort of reminiscent of the or statement weirdness from last class. When we proved that or statement, we assumed that one side of the statement was false, and that meant that the other side just had to be true. Something similar goes on here. We know that Q is false, and we also know that one of Q and R are true. So Q or R is true, Q is not true. That means R has to be true. So it's not A. Next up, we're going to check out statement B, not P. And with this, we use a technique from, again, the readings and or previous discrete math course called taking the contrapositive of a statement. So for any statements P and Q, the implication, if P then Q, is logically equivalent to if not Q, then not P. Be very careful with this. It's not the case that you could reverse them in other ways. It's not logically equivalent to not P implying not Q, nor is it logically equivalent to Q implying P. These later two can still work sometimes, but this first thing is the only thing that's true no matter what, in all cases. So we have that not Q implies not P, not Q, P, not P. What's up next? Another implication trick that you'll need to know for more complicated proofs. something being vacuously true, if the if part of an implication statement is false, then the entire implication is true. As always, more on that in the readings. It's just a quirk of how implications are defined. Since we know that not R is false because R is true, this makes the implication not R then P vacuously true. So we can rule out that too. And then that leaves us with only one statement left, P or Q. We already have not Q. Wait. Oh yeah, and we already actually found out that P is false by showing that statement B is true. So neither P nor Q are true, and thus P or Q is false. Woohoo! Answer P. Oh yeah, if anyone has any questions during these, feel free to just put your hand up, interrupt me. Now we're going to move on to another example. I think they're just these two. And these, but this example introduces, or hopefully reintroduces, another concept that'll be important later, quantifiers, and also mentions predicates, which come up once in the course and have tripped people up before. So I'm going to go over them later when I talk about the first assignment. As I've been off repeating, the real introduction to this stuff was hopefully in a previous discrete math course and is also in the readings. So I won't go too into detail on what these symbols mean, but I'll provide a quick refresher. This sort of backwards E means that there exists a variable x such that, well, what does this mean? That P of x is a predicate, which you can think of as being like a function in code, or method in code, that returns a bool. So So P of x could take the number x and then return true if x is prime, false if it's composite, or 1. Could do the same, return true if x is even, return false if it's odd. You could do this too if you want. I hope this illustrates the point that a predicate is basically any true or false statement that depends on a variable. So P of x is a predicate saying something about x, and Q of y is a predicate saying something about a variable y. So this First, this left half of the implication is basically saying there exists an x such that p of x is true. So there exists a prime number. There is a number that is even, stuff like that. Now, this one for all y, guess I just spoiled that. The upside down A means for all. Q of y is true for all possible y. Don't worry if you don't get that last one. I'm attempting to flex. I might be getting this wrong. I think that's the fundamental theorem of algebra, true for all integers. And here's a much more chill predicate that is also true for all numbers. So this part is saying for all y, some statement about y is true. Now, this example is about finding the contrapositive of that statement. And recall that for a implication if P then Q, the contrapositive is if not Q, then P. So we're going to basically negate these two parts of the statement and then just find that in the list of options we're given. So how do we negate a statement with quantifiers? Well, we have, for starters, for all x, P of x is true. If you wanted to convince me that this is false, what would you be telling me? There is not a single x, not ever, you'll never find one, that makes P of x true. Maybe I could be trying to say, my statement P of x could be, in more grounded terms, student X is on the wait list for the course, not actually registered. And I'm saying there exists one of you, at least, is on the wait list. If you wanted to prove me wrong, you would basically have to go through every student in the room and then tell me that they're all registered in the course. So I'm saying there exists a student on the wait list. For that to be false, then all students would have to be not on the wait list. So miraculously enough, that's that example about the waitlist is exactly how it works for mathematical logic. The negation of there exists an x such that a predicate is true is for all x, the predicate is not true. So we can actually rule out these two because, oops, I should have put a not there. Their right side of the implication has an existential quantifier. No good. So let's negate this. For all y, q of y, I'm just going to keep going with that earlier example. Let's say q of y is also saying that a student y is on the wait list. And this time, I'm going kind of crazy. The waitlist situation is really that bad. I'm saying all students are on the wait list in this room right now. That's hopefully wrong. I hope the waitlist situation isn't that bad. For my deranged statement to be false, what would have to be true? To disprove that all students in here are on the wait list, you would only have to show me one student here who is not on the wait list to disprove my assertion that everyone's on the wait list. So to express that, we use the existential quantifier. There exists a y such that the predicate is not true. I know it's this one because it has an existential quantifier. Woohoo! Whew. Ended up with just enough room to say that. Cool. So yeah, this is the answer to that. Just noting how a contrapositive works and also how to negate existentially quantified statements. This is the example from last class. I don't know why it's here. I'm going to skip it. Oh no, it's slightly different. But it still covers techniques that we've seen before, so I'm going to sort of gloss through this. If you're proving an if-then statement, if you're told that if some condition is true, then some other condition is true, you do what my discrete math teacher calls assuming the if. You just add the if part to the assumptions that you're making. So for the sake of this proof, we're going to assume that x plus y equals 10 and that x is less than 0. Using these, we'll prove that y is greater than 10. And from there, we have the reason I initially thought that this was a repeat of an example from last class. It kind of takes on the exact same form. We assume a value for x as described earlier, rearrange the equation to be in terms of y, and then solve for y within an inequality to get exactly what we want. Yeah, there's not much more I can do to expand on this. Solve for y, and then you get the exact conclusion that you wanted. I guess it's worth noting that the concluding statement is a bit different. Just make sure to remember what you're proving. If part 3 said, thus, y is greater than 10, that would be a decent conclusion, but we're proving an if-then statement. It's just nicer to restate the entire if-then thing. Oh yeah, and this one is a similar problem, but works the exact same way. Ooh. Okay, on to the good stuff. We're going to be doing a lot of proofs in this course that look a bit like this. We got quantifiers and an inequality about these quantifiers. So in this case, it's for all natural numbers m, there exists a natural number n such that n squared minus n is greater than m times n. Can you believe this has anything to do with writing programs? It does. You'll see eventually. Something very important to note that some students would mess up in their proofs the last time I taught this course is that you have to address the quantifiers from left to right. They are ordered. So that means you have to do m first and then define n, which is often defined in terms of earlier defined variables, which we can see in the solution happens. So for all m, there exists an n, and we defined n as having a value that depends on m. I'll get more into why we chose that n value later. But I want to Dang it, the thing I'm rambling about isn't really applicable to this statement. It's kind of too basic to mess up. But keep in mind later that it would not be a good idea to define n first and then define m. If we had two existential quantifiers, then I'd be able to illustrate it. I'll get to it eventually. So yeah, second step starts with let n equals m plus 2. How did we get that? Well, it turns out a lot of these proofs just sort of randomly just say stuff, defining variables in ways that don't seem intuitive at all. Let me just skip forward to later in this very lecture. Let n equals log base 4 out of 3 of 2 over m plus 1. That's in the second sentence of this proof. What's going on? Well, these proofs tend to involve a lot of behind-the-scenes work to figure out what values you're just going to pull out of your hat. And to find what values you want to use, you sort of have to reverse engineer the inequality that you're working with. Assume that it's true. Solve for an existentially quantified variable. And then, once you have a value that seems to work when you assumed that the inequality was true, use that value to prove that the inequality is true. So let's start with this. Because of the quantifiers and how they're ordered, I know that m is going to be chosen arbitrarily. I need to show that this is true for all natural numbers m, so I can't assume anything about m. But I can and should choose a value for n. So my algebra is going to involve solving for n in terms of m. So I'm just going to pick away at this. Maybe I'll factor out n. This is looking a bit nicer. Maybe I'll divide both sides by n. This is looking a lot nicer. And add 1 to both sides. So we see that this inequality implies that n is greater than m plus 1. So that's our start. That is our rough work. If and when you're doing something like this on a quiz or an assignment, you would scribble this in the margins or in your notebook, but it wouldn't be what you're handing in. You haven't proved anything yet. But this gives us an excellent foundation to work off of in our goal of finding a value for n such that the inequality is true. We know that n has to be greater than m plus 1. Well, what's a natural number that's greater than m plus 1? M times 2 billion would be a valid guess, yes. It would be a correct guess. The values used in these proofs are never the one definitive right answer. The markers hate these. There are many different values you can choose to prove these statements. You only have to find one. So I'm not going to go with n equals m times 2 billion, even though that is greater than m plus 1. Yeah, it definitely is, because m is a natural number. I'm going to say n equals m plus 2. Cool. So now that we have a value for n, we would go forth and write the formal proof, the thing that you see in the slides. And the process of doing that is basically to define any existentially quantified variables as you are based on what you did in the rough work, and then show that the inequality you're given is true. Usually, this involves starting with the expression on the left and then showing that the relevant inequality applies to the expression on the right. But this is a simple example compared to what we're going to see later in the course. And for that, we can just start with this definition and then sort of expand it into the inequality that we're trying to prove. So n equals m plus 2. This implies that n is greater than m plus 1. which implies, I think it's actually logically equivalent to, that it's greater than, or that n minus 1 is greater than m, just subtract 1 from both sides, which is logically equivalent to product of multiplying both sides by n, and would you look at that? We found the inequality that we wanted to. And what I doodled here is just a quicker, more symbolic version of what we have over here. When you're writing your own proofs, definitely do it more like the slides than my doodles. And as recommended, do a little conclusion. Since m was arbitrary, we see that for all m, there exists an n such that n squared minus n is greater than mn. Cool. You just did your first proof with quantifiers and inequalities. It's going to get so much worse from here. Yeah, this is just, like these comments are basically what I just went over. The quantifiers are addressed in order from left to right. I'll show you why that's important at the earliest opportunity. Our goal is to prove the inequality that we're given. But in order to figure out what values to use for existentially quantified variables, we do start from the inequality and derive the value for n. But of course, that's just rough work. Your proof should look more like what's on the slide. The natural numbers start at 1, and this last little bit is a little exercise. Just change the class, I guess you could call them, of the numbers we're working with. Make it so they can be integer. Make it so they're integers and thus can be negative. Does the proof change at all? Ooh, you can figure it out yourself. Okay, new one. There exists an m such that for all n, if n is greater than m, then n plus 20 is less than n squared. Whew, this is quite a bit beefier than our last one. And our first sentence is let m be equal to 20. Okay. It's not at all clear how the writer of the proof got to that. It would be nice if they explained it. But we don't have the luxury of explanations, although we do have the luxury of being able to reverse engineer stuff. We're going to start with the inequality n plus 20 is less than n squared. And then we're going to solve for n, get a inequality of the form n is greater than something. Spoiler alert, it's probably going to be n is greater than 20. And then we wouldn't be allowed to say let n be greater than 20 because n is universally quantified. This has to work for all n, not just n equals 20. But the process of finding a value for n will still be useful because of this if we're going to find that n has to be greater than something, it's probably going to be greater than 20. And then in order to make that if part true, we're going to say, well, basically substitute the value 20 for m. N has to be greater than 20, m equals 20. So how are you going to solve for n? Might not be immediately obvious. And I guess you could use like the quadratic formula or something, but if you don't feel like memorizing that, then yeah, it looks kind of difficult to solve for n. So this is sort of finally getting at when I talked about this stuff kind of being a new way of thinking. I'm going to do some pretty strange stuff, and we're all just going to have to get used to it. First, I'm going to look at my notes to make sure I'm getting it absolutely right. Oh, yeah. So I think it's very annoying and pesky and bad that this side of the inequality has a whopping 2 terms. If it were just one term, like a number on its own or n with some coefficient slapped onto it, life would be easy. I would just divide both sides by the same thing. But it's not. So sad. So what do? We can actually just make guesses at the value of n. Check this out. I want n to be equal to 20 because that would give us n plus 20 would be less than n plus n, which would be equal to 2n, which is something that is much easier to compare with n squared than n plus 20. I'm actually going to make a new slide, if I can remember how to give myself more space to explain this. Oh. Okay, I'm going to try once more to make it the right page size. If this doesn't work, I'll just give up. There we go. That'll make it so much easier to scroll through later when you're studying. So we can look at this as like a number line. We got n plus 20 over here, and n squared over here. This just comes from our original inequality. N plus 20 is less than n squared. By just making a wild guess that n should maybe be greater than 20, we derive the inequality n plus 20 is less than 2n. So where would that fit into our number line? Well, it would definitely be to the right of n plus 20, because we already showed that n plus 20 is less than 2n. Would it be to the left of n squared? Well, common sense says yes. Your intuition says yes. That is how multiplication and exponentiation work. But we haven't proven it yet. So 2n could be like anywhere in this number line. And so we have this. We know for sure that n plus 20 is less than 2n. We proved that. And we also know that n plus 20 is less than n squared. But we don't know if 2n is less than n squared. If we can show that 2n is less than n squared, then we'll be able to just use that as the inequality that we're assuming in order to find values for n. And anything that we find from assuming that inequality will be applicable to if we were working with the original inequality, because it came from the original inequality. So we have this. We can divide both sides by n, I guess. To get this. And this isn't much of a conclusion, but it's enough for what we are trying to do. Remember that we're trying to prove that this whole monstrous thing is true, and that involves finding the value for m such that the statement or the inequality is true for all n greater than m. So we basically just played around with that inequality a little bit, found that n should probably be greater than 20, and n should probably be greater than 2. Luckily, both of those conditions are covered by n being greater than 20. We haven't proven anything yet. This is all just exploration, trying stuff that you think might work. But once you're confident enough that you've found relevant values for the existentially quantified variables, you can move on to writing the formal proof. So as explained earlier, we found that n should probably be greater than 20. The statement involves if n is greater than some m, and m is exponentially quantified. So setting m equal to 20 allows us to proceed with our proof. So we let n be arbitrary, lines up with our quantifier. Suppose that n is greater than 20. This is the lesson that came up earlier in this class about assuming the if. So now we have n is greater than 20 and also greater than 2, which allows us to do the thing that I talked about earlier. Basically, starting from the expression that's on the left of the inequality, and then just doing algebra on it to arrive at the other side of the inequality. So I recommend doing a bit more detail than these slides when doing your own proofs. This is sort of minimalist, just saying that, oh yeah, n plus 20 is less than n plus n, which is equal to 2n, which is less, blah, blah, blah. It's good to justify why and how this algebra works in order to make a clearer proof that the statement is actually true for the values that you chose. So let's continue. We'll need one more justification. N plus n equals 2n. That just works because multiplication and addition just work like that. But 2n being less than n plus n, that only works since we know that n has to be greater than 2. And then n times n equals n squared. We ended up getting our original inequality from all this mess. And that concludes the proof. Sorry, it completes the proof. Oh, yeah?
In the previous example, we used a minimal case where we went n is greater than n plus 1 plus n plus 2. We don't use a minimal example in this one. Like n could be 6.
Oh, yeah.
Quality holds.
Ooh.
Makes sense, plus 130.
Yeah. Wait. I think n has to be greater than 20 for this exact logic to work, specifically this step. But I don't doubt that other values are possible. M being equal to 20 is just one possible outcome. Anything greater than 20 would obviously work because that first step would work exactly as described. And while I haven't completely convinced myself of this in my head, I can see it being very reasonable that there are values of m less than 20 that can work for this. This is just one example. Oh yeah, so basically, restate the thing that you wanted to prove, say that you just proved it, and you did it. Cool. Get used to doing stuff like that. Yeah, your entire mathematical education up to this point used equal signs exclusively. It's pretty likely that none of you have experience manipulating inequalities less than and equal to, or less than and greater than, like this. It's going to get weird. There are going to be things that I do that make no sense, but you'll get used to them. And also, when I do those things, it might be completely indistinguishable as to whether I'm making a mistake or whether I know exactly what's going on and I'm just doing some like galaxy brain stuff. Put your hand up to clarify, because it totally might be a mistake. I think this is an okay time to talk about ordering of quantifiers, although I can't quite think of an example of a erroneous proof using this non-technique. I can still show you what not to do. We have for all m, there exists an m such that for all n, blah, blah, blah. So we defined m with a specific value. If we said something like, let m equals n plus 1, the marker would be very sad. Don't make the marker sad. Because the quantifiers are ordered such that m is defined before n even exists. It's like if you're writing code, you can't say something like int a equals b plus 1 and then define b. This won't compile. Exact same logic as for why this declaration of int a won't work is the same as why you can't say let m equals n plus 1. Putting quotation marks around this just to make it like clear that I'm not actually making this part of an example. I'm like writing m equals n plus 1 and shaking my head the whole time so you know that I know that it's wrong. Yep, there are other values for m that can work. And I think this little shortcut is going to be introduced here and used for basically the rest of the course. The sets that these numbers we're working with belong to is usually just clear from context. We're not going to write for all m and n, or in the natural numbers, for all n in the natural numbers anymore. We're sometimes going to assume that numbers are in the natural numbers. Sometimes we're going to assume that the numbers are in the real numbers. Either way, eventually this will become applicable to stuff that's a bit more grounded in computer science. And when we have that context, it'll be clear what sets the numbers belong to. And this slide has some exposition on the general technique that we just did. For those of you writing notes in addition to what's on the slides, I recommend making a little section to the side detailing some tricks to use, because this is the rounding up trick. And there are going to be several more slides in the future that go like strategy. I call this the whatever trick, along with a description of a general technique. And it basically comes down to choosing n large enough to round up to a constant term that we have in our inequality in order to make it simpler. Crucially, the simplified inequality has to be between the two original sides of the inequality. Just a really unsatisfying explanation, I know, but just so it works. If instead of n plus 20 is less than 2n, you found that n plus 20 is greater than n, and then you compared n with the big side. The simplified side you found would be to the left of the original, and then anything you find based on that new simplified inequality wouldn't necessarily apply to the original. That's something that trips up students too. And it's the sort of thing that is difficult to wrap your head around at first, but if you do lots and lots of examples, I promise it'll be ingrained into your intuition eventually. The simplified side of the inequality needs to be between the original two sides. Okay, so in this one, we're assuming that everything is a real number. Kind of contradicting that thing about the shortcuts earlier, but whatever. Like I said, eventually this will become more grounded in actual computer science, and from there it'll be clear when you're working with natural numbers and when you're working with real numbers. Okay. For all m, there exists an m such that for all n greater than m, this is true. This means that our goal, starting from the original inequality, is going to be to find a statement in the form of n is greater than something. And then, because of the quantifiers we're given, we're going to set m to whatever that something is. And then once we've set m, we show that this value for m leads to the rest being true, and that proves the statement. Just like before, the order of quantifiers matters, so don't you dare say something like, let m equals 2n. Nuh-uh, don't do that. It's like int b. So let's do some rough work. Remember, this stuff's all going to be like scribbled in the margins of your paper, not handed in. We have 8n squared plus 5 and n cubed. I want to solve for n, but this plus sign is really annoying. Sure would be nice if I could have 8n squared plus 5 just be one term, which would allow me to more easily compare it to the other side. And remember, my goal is to find a value for n, and as such, it's totally valid to guess a value for n. And then if it turns out to work, you just write stuff like this and pretend that you knew what you were doing the whole time. So I'm going to try n greater than 5. I see a 5. That's a constant. I don't like the constant. Oops. Okay, better. This gives me something to work with. I could maybe factor out an n, divide both sides by that, and keep going. Actually, I'm going to try that. This isn't the strategy that I was planning to show, but I think it'll actually work. Okay, yeah, we're just left in a similarly inconvenient situation. Maybe I could set n to 1 and then do the same sort of substitution. Yeah, that'll probably work. Oh my God, it's totally working. Going totally off script, but ending up with the exact same conclusion that I was going to go towards from the start anyway. I'm going to finish up this and then show you what you were not supposed to do, but what I was planning to show you. It all just goes to show that there are multiple solutions to every problem. 9n is less than n squared. 9 is less than n, which means that n is greater than 9. We have to show that n has to be greater than some specific number. So we set that specific number in question to 9. Cool. Yeah, that was fun. But the thing that I was going to show you, perhaps quicker, was to just do this in one guess of the value of n instead of 2. What? Okay, the plan for this example was to turn that plus 5 into plus n squared. And how would we do that? Well, stupid thing. We would suppose that n is greater than the square root of 5, which would imply that n squared is greater than 5, and thus allow us to just substitute n squared for 5. But it gets worse, better, I don't know, cooler. We don't even have to make a separate guess that n is greater than root 5. N being n being greater than 5 also implies that n squared is greater than 5. Like, you're just squaring it. Yeah, it still works either way. Oops. So 9n squared is less than n cubed. And we reach the same conclusion as before. N is greater than 9. So we ended up with a whole bunch of different properties for n that may or may not be true. We have that maybe n is greater than root 5. Why isn't my undo button working? Oh, now it is. Huh. In our other, probably simpler attempt at the question, we suppose that maybe n is greater than 5 and n is greater than 1, and ended up with n being greater than 9. Remember, this is all rough work, attempts at finding a value or conditions on n that work. But in all of these cases, we found that setting n to be greater than 9 sort of covers our other assumptions that maybe n is greater than 5 or n is greater than 1. That's just because 9 is greater than 5 and 1. So instead of saying that, like, suppose that n is greater than 9 and also n is greater than 5 and also n is greater than 1, we just use the simplest value that covers all of the properties that we guessed earlier. N is greater than 9. So with this in mind, we just set m to be equal to 9 and go forward with the formal proof. With these kinds of questions, the rough work is the hard part. It's kind of weird. Once you have your value of whatever existentially quantified variables there are, I don't want to call the rest a cakewalk, but it's much easier. You're basically repeating your rough work in reverse. We substitute 5 for n squared since we found that n squared is greater than 5, which came from n being greater than 5 or n being greater than root 5, whatever. Add those up to get 9n squared. Substitute n for 9. And then do some algebra and write a nice concluding statement. I'm going to rush through this last one. It's actually surprisingly simple. Looks very intimidating because of that value for n, but I think I'll be able to do it in 5 minutes. So for this, we're not even gonna make any guesses about n immediately. We're just going to notice that because of how exponentiation works, where should I put this? 2 to the power of n is less than 3 to the power of n. Which implies that 2 to the n plus 3 to the n is less than 3 to the n plus 3 to the n equals 2 times 3 to the n. So that actually gives us our simplified side of the inequality. We can go ahead and simplify the original inequality to say 2 times 3 to the n is less than m times 4n. Rearrange stuff a bit to get 2 over m is less than 4 to the n over 3 to the n. Rewrite that to be a bit nicer. That's just 4 to the 3, or 4 over 3 to the power of n. And then we're solving for n, so take the logarithm of both sides, base 4 out of 3, to get this monstrosity. And I think I don't have time to talk about the formal proof, but whatever, I can spin this. This is going to be a nice way to study. You have my rough work. So on your own, check out the rough work and try to see how that turns into the formal proof on your own. Yeah, I'm not going to attempt to go over the assignment in 2 minutes, but I will try to post the assignment 2 minutes into office hours, something like that. And I'll go over it in class tomorrow. So good luck in advance, and I'll see you then.